Now let us look into new topic, that is complexity. So the term complexity is not something new to us, right? We have already encountered this term while performing analysis on the algorithms. What we have learned in our lower semester, that is design and analysis of algorithm course. Okay, so here also we are referring to the same thing. See, when I say the program or a language is decidable, I simply mean that the problem is computationally solvable in principle. So in principle, in the sense, in theoretically the problem can be solvable, but practically it may not be possible because it may require a lot of computational time and memory, so which may not be feasible with respect to any computers or any physical devices, right? And any further discussions with respect to the proofs of complexity is solely based on the definition of a Turing machine, and we assume that P is equal to NP. Okay, so P is a polynomial time and NP is a uh, polynomial time in non-deterministic Turing machine. So this is the polynomial time complexity with respect to a deterministic Turing machine, and this is with respect to non-deterministic Turing machine. And most of the scientists, computer scientists and mathematicians believe that P is equal to NP. Okay, and with this assumption, we will look into the various proofs and theorems involved with respect to complexity. And of course, this is not yet proved that P is equal to NP. It is still a questionable, and it is considered to be one of the biggest mathematical problem of 21st century. Okay, so with this, let us look into furthermore concept of complexity in terms of growth function. Okay, growth rate of a function. So why growth rate of a function is required? So see, suppose I have an algorithm, I have a problem, okay, and this problem can be solved by using more than one algorithm, right? So that I can have n number of algorithms. So let me write A1, algorithm 1, and A2. Okay, so one problem can be solved in multiple ways. And how will I determine whether algorithm 1 is better than the other? So that depends on its efficiency. That depends on the growth rate of the function, right? That depends on the time complexity of this function compared to this, right? And this is something what we have already known uh, when we have learned design and analysis of algorithm course, right? Okay, so let us look into the definition. So I have two function f and g, and we can say that f of n, the function f of n, is big O of g of n if there exists a positive integer c and n 0 such that f of n is less than or equal to c into g of n for all n greater than or equal to n naught. So in this case we say that f is of the order g, or f is of big O of g. Okay, so this is how we represent it. Okay, so uh, what we mean is there is a function f of n. Okay, and this is the growth rate for the value n. So as I increase the value n, this is how the function grows, and there is also g of n, right? Okay, and g of n grows in this way. C into g of n grows in this way for n value n naught. Okay, so this is the n naught value. So what does this represent? See, after the value n naught, after the value n naught, uh, f of n, the value of f of n is always less than or equal to c into g of n. Okay, so before this n naught, there is a possibility that c into g of n is less than f of n. But if there exists something like this, then I can say that f is of the order of g, or simply f is big O of g of n. F is big O of g. Okay, f is big O of g. Okay, and we should remember that f of n is equal to big O of g of n is not an equation, it's an expression, a relation. It expresses the relationship between the two function f and g. Okay, so with respect to this, let us consider some examples. Let us consider some example here. In this given problem, f of n is equal to 4n cube plus 5n square plus 7n plus 3. Okay, and they have asked us to prove that f of n is equal to big O of n cube. Okay, so f of n is given. So what is this? This is nothing but the g of n function. Okay, which is n cube, and we have to prove that this is f of n is equal to big O of n cube. So what we have to do? So to prove that, I need to obtain, yeah, so this is the graph how it should look, right? F of n, which in this case it is 4n cube plus 5n square plus 7n plus 3. Okay, so this is the growth order for n, and suppose this is how c into g of n should work, which is nothing but some constant c into n cube. Okay, and this value is n naught. Okay, so any value below or less than n naught, c of c into n cube should be less than f of n function, and for after n naught, the value of c into n cube should be greater than f of n. Okay, so basically some constant into g of n will be greater than f of n. Okay, so now what we have to do is we have to identify whether such n naught exist. Okay, so to prove, let us take c is equal to 5. Okay, so this becomes 5 into n cube. Okay, now I have to identify the n naught value. Let me take it as 10. Okay, now if I take c as 5 and n naught as 10, which is a threshold value actually, then let us see what happens. Then f of n, okay, so for n is equal to n naught, which is equal to 10, what will be the value of f of n? F of n will be 4 into 10 cube plus 5 into 10 square plus 7 into 10 plus 3, which will be equal to 4 5 7 3. Okay, now c into g of n, c as I said is taken as 5 into 10 cube, so which will be equal to 5000. So obviously, if you observe here, f of n is less than or less than when, yeah, it is less than g of n, c into g of n, for the value n is equal to 10, right? So this is the obvious value what we got. Of course, the 4573 is less than 5000, and for any value of n which is greater than 10, f of n will remain less than c into g of n, right? So uh, this graph we have proved, and the condition is satisfied. So we can prove that, or we can say that f of n here is big O of n cube. Okay, and of course the value of c, the n naught value, it depends on the value of c what we have taken. So there's a possibility that we may get different for different c value, the n naught also changes, right? So this is not the only value what we can take to prove that f of n is equal to big O of n cube. Okay, so this is an example of the growth rate of a function. Now let us look into the two class of problems, classes P and NP. So when can I say that a set of problems is of class P? So if a problem can be solved by using a deterministic Turing machine or a deterministic algorithm in polynomial time, then it belongs to the class P. And if it can be solved, if there is a problem or the classes of problem that can be solved by using a non-deterministic Turing machine in a polynomial time, then it belongs to the class NP. Okay, so uh, now it is not proved that NP P whether P is not equal to NP. For time being, it is still believed that P is equal to NP by most of the computer or almost all the computer scientists and mathematicians. And with this assumption, the various complexity related to Turing machines are proved, or theorems and proofs with respect to Turing machines are done. Okay, so let us see some definition with associated with this classes P and NP. A Turing machine M is said to be of time complexity Tn if the following condition holds. That is, given an input W of length n, M halts after making at most Tn moves. Okay, so if I give some input W of length n to the Turing machine M, it halts, either say it will say yes or no after making at most n moves, then the Turing machine is said to be of time complexity Tn. Okay, so what do you mean by Turing machine halting? So when I say Turing machine halts, it will either accept the string or reject the string by making a maximum of n moves. Okay, yeah, and this is the alternation definition. A language L is of class P if there exists some polynomial Tn such that the language is equal to uh, Tm for some deterministic Turing machine M of time complexity Tn. Okay, so this is about the two definitions with respect to classes P and NP. Now let us calculate the time complexity of a Turing machine by considering some examples. Okay, so here construct the time complexity Tn for the Turing machine M. Okay, 0 power n, 1 power n, where n is greater than or equal to 1. Okay, now what we have to do is we have to calculate the time complexity, that is the number of steps that is required to solve this particular problem. So that depends on the string W, right? So not only it depends on W, it depends on length of W. Yeah, when I say it depends on W, yes, of course it depends on the length of W, which will be treated as n. Okay, so how this can be solved? We have already solved this problem. Okay, let me consider an example. So I have, let me take three zeros and followed by three ones, which satisfies the definition of the language. And how did we solve this particular problem? To understand how this works, I suggest you to go back to the previous lecture videos. We will understand how this is solved, right? Okay, so this is solved by marking 0 as x and looking for y, and looking for 1 and marking 1, the leftmost one as y. Okay, so the leftmost 0 is marked x, and after marking it as x, then we look for the leftmost one and it is marked y, then we come back looking for the second 0. So how many moves did we do? So in the process of looking for the first leftmost one, we made n moves, right? And after making this n moves, we come back, right? We come back up to x. So another n moves is made for a single occurrence of 0 and 1, right? So totally how many moves did we do? 2n for 2 into n for one occurrence of 0 and 1. Similarly, how many times this has to be repeated? This has to be repeated based on the number of zeros, which is equal to n. So total moves made will be 2n into n. So which is equal to, at most I have to make a 2n square move. Now we all know that we can 2 is a constant, right? So I can simply write this as the time complexity of the Turing machine as big of 2 into n square, or this can be written as, we can ignore the 2 since it is a constant, so I can write this as big of n square. So this is the solution for this is the time complexity solution. What did we have constructed based on the solution approach what we have followed, right? Okay, so the solution is big of n square for a Turing machine for the problem 0n 1n.